Okay, so now we're going to look at some rotational mechanics. We're going to start off by looking at one of the old school bikes called a penny farthing, usually. They look something like this. And then they have the little handlebars up here. Yeah. The radius of these laughable little vehicles, the radius of the wheel there is, that almost looks like a 3. 0.5 meters. The wheels themselves were about 1 meter in diameter, at least with some of them. You had fluctuations, some bigger, some smaller. One might wonder why this was the case. I should actually look it up and double check, but they didn't have gears often on them. And so for turning the pedals once, we'd actually end up with a pretty good physical displacement. So since they don't usually have gears, I'm pretty certain that's why they had such a ridiculously large wheel. Turns out gears are probably a better way of going about it, hence why modern bicycles don't really rely on that design. But we're going to look at asserting that this particular penny farthing, the angular frequency, the angular velocity of the wheel here, follows the following equation. 2 plus 4 times t squared, where t is the time in seconds. And we want to know how far this bike goes from t2 to t3. Okay. Well, the first thing we can do is we know that this is... Actually, there are two ways of looking at this. The way that comes to mind immediately for me is that omega equals d theta dt. And we'll do the old trick of separation. And that gives us, moving it around a little bit, we have d theta equals omega dt. We're going to integrate both sides, adding up all of those little pieces. And we are going to evaluate this along a t of 2 to 3 seconds. And so replacing this, we'll have, over here we're going to have delta theta, because we're going to go from theta initial to theta final. And we're going to go integrate this from 2 to 3. So delta theta, final minus initial, equals 2 plus 4t squared dt. Spreading those out, we're going to end up with delta theta equals the integral of, forgot my integral there, 2 dt plus the integral of 4t squared dt. Both of these are evaluated from 2 to 3 seconds. Okay, and that'll get us our change in theta. We'll go ahead and evaluate this. We know that delta theta equals, we're going to go with 2t evaluated from 2 to 3 seconds, plus, looks like 4/3 t cubed, also evaluated from 2 to 3 seconds. Okay. Well, I can go through and I can evaluate this. Let me see if I've actually got that, or... Okay, it looks like I went ahead and used... Yeah, that should be fine though. Okay, so evaluating these, we're going to have delta theta equals, well, 2 times 3, that's going to be, so this will be 6 minus 4 plus, this one's going to be a little more complicated. We're going to have, when I plug 3 in there, we end up with 27 divided by 3 is going to be 9 times 4, that's 36, minus, do the same thing with 2, we're going to have 8. 8 times 4 is 32. I hope I'm doing that correctly. 32 looks about right. Okay, so I'll have delta theta equals 2 plus, well, that's irksome, 36 minus 32 divided by 3. I'm just going to do this the simple way. we end up with about 25.3 repeating. And I don't know why I say about when I give the actual value. This tells us how many radians we have swept through, but that doesn't tell us an actual physical displacement. I want a physical displacement of this bike. So I'm going to use one last relationship where theta equals our displacement over r, or looking at it another way, our displacement equals theta times r, the angle that we sweep through, multiplied by the radius of the circle. Now, this is one of the reasons we can use this to see why we constantly use radians and not degrees, because of this relationship. You can see that this is nothing more than, hopefully you've seen this equation before, s, which is usually for arc length, theta times r, where theta is in radians. It gives us an arc length. So if I've got theta here, this arc length, s, equals theta r, where theta is in radians. That doesn't work when you're using degrees, and this is why in rotational mechanics we pretty much always deal in radians, because it makes it very easy to use these relationships here to go from our linear to our rotational. So we're almost done. We have our value for theta here, so if I just multiply through by r, delta theta times r equals delta x, which is going to be nothing more than 2 plus 25.3, which will be 27.3 repeating, times our radius, which is 0.5 meters, and we end up with delta x should come up to 13.6 meters, thereabouts. There we go.